Hello, thank you for attending this presentation. This work, which was initially published in the journal Empirical Software Engineering, was a study of the team structures in social coding platforms, particularly GitHub. The work was performed by myself, my previous colleague Dr. Zhang, and my supervisor Dr. Zhu. Social coding platforms such as GitHub have become a popular means for developers to collaborate in a virtual manner. At the heart of the social coding platforms is the pull request feature, which allows developers to submit code contributions that are reviewed and possibly integrated into the mainstream of a project. To examine how developers self-organize while using the pull request feature, we define a collaboration between developers in this context as what we call a contributor-integrator relationship. Two developers are linked if a contributor submits a pull request that is evaluated by an integrator. This definition of collaboration also entails that the relationship could be bidirectional, as developers can act as both contributors and integrators, and the link between two developers can also be weighed by the number of times that this type of collaboration happens, which is essentially the number of pull requests. What we did next was select a number of projects from GitHub that adopt the pull request model, so 7,850 projects in total, and for each project we built its associated pull-based network, which is a weighted and directed graph. Then from the pull-based networks we compute a set of network metrics. Before moving forward to the RQs, let us see a few examples of the network metrics that we computed and what they mean in this context. Starting with the density, which measures the sparsity of connections in a graph. In this context, it measures the tendency of developers to collaborate with many teammates, reflecting a dense network, or only a few, reflecting a sparse network. Then we have centralization, which measures the presence of central nodes or developers based on either incoming or outgoing edges. When we are dealing with incoming edges, we are capturing the presence of central integrators, while outgoing edges measure the presence of central contributors. And then we have reciprocity, which measures the likelihood of nodes in a directed graph to be mutually linked. And in this context, it basically measures the tendency of developers to act as both contributors and integrators. With this data at hand, we try to answer our first research question to find the influential network metrics on the performance of processing pull requests. So for each of our subject systems, we had two pieces of data at hand. On one hand, the network metrics that basically describe the structure of the project team, and on the other hand, a set of metrics that capture the performance of the team in processing the pull requests, such as the response time and the processing time. After applying a regression model, we find a strong association between the metrics density, out-degree centralization, and reciprocity on the performance metrics. In other words, we find an association between faster response and processing time of the pull request and developers taking multiple polls and collaborating in a dense manner. Next, we attempt to capture the different structures that are formed by the developers when they use pull requests. So from the pull-based networks of the project, we infer the existing, frequently adopted team structures by first normalizing the significant metrics identified in RQ1 and then transforming them into an n-scale representation. Here you can see the normalized distributions of the significant network metrics. For example, the distribution of density leads us to adopt a 3-level scale to discretize the density values. At the end, we end up with 18 possible team structures. Here you can see examples of some of the most team structures that we identified and that we encoded in the form out-degree, centralization, density, reciprocity. 311, which is present in 19% of the projects, describes a centralized network with sparse connections and low reciprocity, as reflected by the values encoded in the name of the team structure. And 331 or 332 is a centralized network that is densely connected and also reciprocal. To conclude RQ2, we were able to infer different team structures and identify the most common ones. We further group them into the following: sparse team with multi-role developers, sparse team with single-role developers, and well-connected teams with core contributors. The next logical question is what's better and what's worse? We ordered the inferred team structures based on the associated performance metrics, such as the average processing time that you can see here. Some team structures such as 331 and 332 were consistently at the top, while others such as 111, essentially describing a network with low centralization, low density, and low reciprocity, ranked at the bottom of the list. The conclusion was that the projects whose teams are well connected and are centralized around core contributors are associated generally to more efficient processing of the pull requests. So far, our analysis has been static in time, so for our final RQ, we study the evolution of the team structures over time. For the example shown on the slide, we find that it is 5 times more likely for processing time to improve when the team structure itself improves after a span of 2 years. More examples and details are included in the paper. Overall, we observe that the transition of a team towards a structure that is more centralized, more dense, and more reciprocal is generally associated with a significant improvement in the speed of processing the pull requests. To conclude, what does this mean in practice for the practitioners? We identify that some team structures are not so good. Digging deeper into what sets apart these team structures, we find that they are characterized by the formation of cliques and by an increasing number of drive-by contributors who never commit to the projects. So these two observations can be used as warning signs that the current situation is not the best. What can be done? Based on our finding, we recommend that the maintainers of projects try to create explicit mentoring relationship between new contributors to avoid that they become drive-by contributors, and established developers within the project to build trust and favor retention, and also to maintain a central core within the team despite the team growing in size. To summarize, this study looks into structures of team as they use the pull request model on GitHub. Some structures are better than others in terms of the performance of processing the pull requests. And with this, I end my presentation. I thank you for your attention, and I am glad to answer any questions you may have. Virtually in person.
Okay,
yeah.
so I guess we're live now in the Q&A.
Perfect.
So if people have questions, please type them into the chat. And I have some questions, but I want to give the audience a bit. Okay, so here are a couple of questions.
Yeah, so
what is the definition? The drive-by contributor.
So basically, a drive-by contributor is a developer who would not commit to a project. Basically, they would submit a pull request, meaning a code contribution to the project, but would never come back. So basically, it's a one-time or two-time participation to the project, which is not ideal because project maintainers would ideally want people who would commit to the project, who would submit frequent contributions.
And kind of a follow-up on that from Igor is, were there cases in which a high number of drive-by contributors caused problems? Did you actually see problems arising from that?
So it causes problems in the sense that a drive-by contributor is basically a person who is unknown to the core developers of a project. So there is less trust. So whenever a pull request from a drive-by contributor is being evaluated, it will take more time because the person is unknown to the project developers. And so there is less trust and more likely a higher processing and response time, versus when we notice that two developers have collaborated more in the past, it is more likely that the pull request will be processed much faster.
And a similar question from John. Were there negative characteristics or other characteristics of cliques?
Yeah, so basically we noticed that when we came up with those different team structures and we ranked them from best to worst, we noticed that the team structures that are associated to the worst performance metrics, meaning higher processing time, higher response time, etc., were more had more presence of cliques, So we inferred that the presence of cliques, so where people are, so basically where we have clusters of people that do not necessarily communicate between each other, also led to lower values in terms of the performance metric that we were measuring. So it's likely an indication that the team structure is not as good as it could be to support a more efficient processing of the pull requests.
And Paul asks, which is a question that I had as well, you talk about teams that you've discovered from the network relationships. Do these correlate with the more traditional notion of a team, people who are working together on the same project or in the same area or whatever?
So yes and no. So when I talk about teams in this context of GitHub and specifically working with pull requests, a team is composed of all the developers that have either contributed with a change to the project, a code contribution, or have evaluated the code contribution that was submitted by someone else. That would include the people that form a team in a traditional manner, like the traditional notion of a team, but also some people who come and go, which we refer to as drive-by contributors, which would not traditionally be considered as part of a team. So I hope that answers the question.
Do you think if you looked to the nature of the teams behind the networks, the actual organizations and so on, that you might see differences in that might have some effect on what shows up in the network and in the performance?
So I think the main thing that we may be missing when we are trying to capture teams in this context is that based on what we observed in the projects, there are some team members who do not have to go through pull requests to actually make contribution to the project. They can make commits directly to a project without going through the pull request process. So that's what we might be missing when we are discussing the notion of teams in this context.
Okay, a question from Igor. Have you analyzed the characteristics of the projects as well? Projects with different governance models, financial support language, and so on. And do you see any results from things you might observe about the projects?
I wouldn't say we have
Excuse me, we have to go.
Oh,